Okay.
Just a delay there.
Should we start? Okay, so it's a pleasure to have Ben Lackey. His title, mysteriously, we didn't know about it until now. What can we learn about neutron-star equation of state from inspiring by neutron-star?
Okay.
So you have 30 minutes roughly.
All right. Yeah, so this is work I've been doing with Wes Wade, who's in Milwaukee right now. So I'm going to just go into more detail about what Satya talked about yesterday with using these tidal parameters to measure the equation of state. So essentially the idea is each neutron star creates a tidal field, and that induces a quadrupole moment in the other star during the inspiral. And the amount of deformation you get is dependent on this tidal deformability parameter. So times the tidal field. And this is essentially roughly equivalent to the radius. So this is the Love number, K2, which is some dimensionless quantity, times the radius to the 5th power. And so what I'm showing here is just the radius as a function of mass for several different equations of state. And here is the same equation of state, but the tidal deformability parameter. So essentially, it looks like very similar behavior, slightly different. They scale in the same way, so stiff equations of state with large radii have large tidal parameters. Soft equations of state have small radii and small tidal parameters. And just for reference, the masses in known binary neutron star systems I'm showing here, there's about 10 of them. They range roughly between 1.1 or 1.2 and 1.5 or 1.6, something like that. So that's just a reference. And then there's also high mass neutron stars known in neutron star white dwarf binaries. They're around 2 solar masses with fairly small error bars. So the way the tidal interactions affect the waveform is through these tidal parameters that enter at 5 post-Newtonian order. So it's technically a Newtonian effect because you just, in Newtonian gravity, you have tidal interactions. But the way it affects the waveform looks like, so here I'm showing the Fourier transform of the waveform. You get a typical, this is a chirp mass times frequency to the -7.6 times a phase term, psi, where you have time and phase of coalescence, and then this leading order term here. Then you get point particle post-Newtonian terms, and then at a power of v to the 10th power, you get your leading order tidal correction. So that looks like a 5th post-Newtonian effect. And it's a linear combination of the 2 tidal parameters from each star. So here I'm showing you this quantity lambda tilde. This is the tidal deformability of one star and the second star, and it's weighted by the symmetric mass ratio. And what I'm showing you here is just what the waveform would look like. The black curve is if you don't have any tidal interactions, so if you have a binary black hole waveform. And then the red waveform is if you have a fairly moderate equation of state. And this is the leading 5th post-Newtonian tidal correction. So up until the last 20 or so cycles at about 400 hertz, you have a very small amount of phase shift on the order of a radian or so. And then through the last 20 or so cycles up to ISCO is where you get most of the tidal correction. And it's about a cycle for the gravitational wave phase shift. So what I'm going to be talking about is how we measure the equation of state if we can measure the tidal parameter. So what I'm showing here is just several different equations of state. Pressure is a function of density. There's about 30 different equations of state here. There's a fairly wide range of pressures here. These are strange quark matter equations of state. I won't talk about these, but then there's several other kinds of equations of state. And what I'm going to do is come up with a parametrized equation of state and then try and measure those equation of state parameters. So the one I'm going to use is a piecewise polytrope, where in a given density region, you have a polytrope which is defined by the adiabatic index. So in 3 different regions, gamma 1, gamma 2, and gamma 3, there will just be 3 parameters for the adiabatic index. And then an overall pressure constant at about twice nuclear density. And that roughly corresponds to the radius of the neutron star. So there's a fairly accurate scaling relation. It's radius pressure, or radius pressure to the 1/4 gives you the radius, something like that, I think. OK. And that's at about twice nuclear density. So that's what I'm going to see if we can do. And there is already some information known about the equation of state that you can translate into estimates on this equation of state parameter space. So one is that the equation of state always has to be causal. So the slope of the equation of state is essentially the speed of sound. So speed of sound is dp d epsilon, the square root of that, and that has to be less than c. And so that rules out a good fraction of this parameter space. So this is 2 adiabatic indices, gamma 2 and gamma 3, and then this pressure constant. And then we also know that the maximum mass has to be at least about 2 solar masses. So then that rules out a good fraction of this region right here, so this light gray region. And here I'm just showing you a constraint if 2.4 solar mass star is observed. So what I'm going to be doing is looking at taking many observations of binary neutron star systems and seeing how well you can measure these equation of state parameters. So something like this was already done. Satya just talked about it yesterday by Walter Del Pozo and others, where they took multiple observations, about 50 binary neutron star observations, and tried to see how well you could measure the tidal parameter at a specific mass of 1.4 solar masses. What I'm going to be doing is similar, but I'm going to parameterize the equation of state instead of the tidal parameter as a function of mass. And this is very similar to work that was done by Andrew Steiner, Jim Lattimer, Ed Brown, where they used multiple mass and radius observations to measure a parameterized equation of state. Here, what I'm going to be doing is just using, instead of mass radius, using the measurements of the 2 masses of the stars and then this weighted tidal parameter for several BNS systems. So what you do is for each binary system, you estimate the waveform parameters. And those are the standard parameters, the sky position, alpha and delta, the orientation, distance, time and phase of coalescence, and then your intrinsic parameters, the 2 masses, and then the tidal parameter. So you can either write this in terms of M1 and M2 or these chirp mass and symmetric mass ratio. And you can estimate this posterior with either a Fisher matrix approximation, or you can do a full MCMC simulation using the Codzine-Lau. And then once you've done this, what you want is just a marginalized distribution over the parameters you care about, which are the 2 masses and then the tidal parameter. So you just marginalize over the other parameters, which is trivial to do with either Fisher matrix approximation or a MCMC simulation. And then the next part is, given that we know, or our estimates of the masses and the tidal parameter, we want to find the equation of state parameters. So again, you do use Bayes' theorem to estimate your parameters. And in this case, it'll be our equation of state parameters, which are P1 and then the adiabatic indices, and then the masses for each of our n systems. And so to do that, you write down the likelihood. And this ends up just being the product of the marginalized distributions for each of your n systems. And to get it in terms of equation of state parameters instead of this tidal parameter, you just write lambda tilde as a function of your equation of state parameters. And then again, you just run a MCMC simulation. This time you have 4 plus 2n parameters. So 4 is the number of equation of state parameters. N is the number of systems you have. So there's 2 masses per system. And then you just marginalize over your masses to get the equation of state
My
parameters.
apologies, before you go on, can you tell me the d sub i's, I lost track.
Oh, so that's just the data from each event. So your gravitational wave data, that's the,
Presumably some signal plus a lot of noise.
yeah.
Okay, all right.
Yep. So the gravitational wave data, so you have the binary neutron star signal plus the noise. So this is simulated noise. So either with an MCMC simulation, you can simulate Gaussian noise with given a the waveform. Couple of things. The one we use mostly is Taylor F2 waveform, Taylor T4, Taylor T1 waveforms. So I'll talk about that later. Okay, so what we want to do is figure out how accurately we can measure the equation of state and other properties such as the radius or tidal parameter given all the observations. So what we did was simulated a population of events. We chose a couple different populations. The one I'll talk about here is, you have to pick a true equation of state because there's no actual data. So we chose this MPA1 equation of state, which is a moderate equation of state. It's about 12 kilometer radius, maximum mass of 2.5 solar masses. And then we sampled a set of systems, 50 systems that have a SNR greater than 8, and we chose them uniformly in volume, distributed uniformly in masses from 1.2 to 1.6 solar masses. This is fairly reasonable range, and this is more reasonable than the stuff done in the Del Pozo work where they chose 1.0 to 2 solar masses. So that's not a particularly realistic range of masses. So that would give better results, but I'll show here that by using the equation of state parameters instead of parameterizing the tidal parameter, you actually do quite a lot better even with a more realistic range of masses. And then we sampled uniformly in volume, uniformly in orientation, and then you calculate the tidal parameter given your true equation of state. And that's how you can generate the population of events. So here I'll just show results for a single event that's drawn randomly from this distribution. These are the marginalized distributions for the parameters. So this is P1, the pressure at about twice nuclear density. You can sort of measure it to a factor of 3 or 4 with a single event. You can't really measure the other parameters. But then if you have 5 events, the errors get smaller. With 20 events, they get even smaller. And then with 50 events, they get quite a lot smaller. So what's probably more interesting is the equation of state, the pressure as a function of density. So you can do a very similar thing where you measure so each set of points in your MCMC simulation tells you what the pressure at a given density should be. So if you want to draw your confidence regions, find what is the pressure at a certain density, you just make a histogram from your MCMC simulation and you draw your 95% confidence bounds or whatever bound you want. And that's what I'm showing for a single event here. And then this is the error, the pressure over the true pressure as a function of density. So the single event, you can only measure this to about a factor of 2 or 3. With 5 events, the errors get smaller. 20 events, and then 50 events, they get quite a lot smaller. And these bumps are just, this is an old simulation, so it didn't quite converge, but I've repeated this and it smooths out. These features right here are due to the choice of parameterization. So we had fixed dividing densities, and that leads to these peaks right here at the dividing densities, and then the region where you match to the low density equation of state. So this is the parameterization dependent. So
if I look at the high density region, you don't really see a whole lot of a difference between 1 and 50 binaries.
yeah, so that is So most of the information is coming from the prior. So most of the density in most neutron stars is around twice nuclear density roughly. So you get the best estimates of the equation of state around those densities. And then you don't get a very good estimate at higher densities. Most of that information comes from high mass observations, so the 2 solar mass prior that we used, or the causality constraint. So that's why it doesn't really improve at the very highest densities. Yeah.
To clarify that, you only include inspiral portion, and you do not include any hypermassive neutron stars or whatsoever. So I think you cannot constrain gamma 3 as a natural.
Yeah.
And what kind of prior are you using for a prior probability? For example, you exclude a causal equation of state, or
Yes.
what for other parameters of equation of state?
So we exclude anything that's acausal. So when the speed of sound is greater than the speed of light, up to the maximum possible neutron star mass or maximum central density.
You also rejected any equation of state which cannot support 2 solar neutron stars.
Yeah, so that's what we do. So that's where most of the information at the highest densities comes from. So yeah. So you can do this, given your equation of state parameters, you can do the same thing with measuring the radius as a function of mass or the tidal parameter as a function of mass. And so again, you just, from your Markov chain points, you just calculate what the radius would be at a given mass and then make a histogram and then draw your confidence interval. And so this is a single event. You can measure the radius to about plus or minus 2 or 3 kilometers. And then the tidal parameter, the error is quite large for a single event that's just randomly drawn from your sample. If you have 5 events, they get smaller. 20 events, even smaller. And then with 50 events, which depending on event rate could be a little over a year, maybe 2 years, something like that, or even higher, much lower, who knows. Then the radius you can measure to about half a kilometer at a given density or a given mass. And so the samples that we chose are from 1.2 to 1.6 solar masses. But because we parameterize the equation of state instead of the tidal parameter or the radius, you can actually measure the radius at a wide range of masses and the tidal parameter for a wide range of masses. And this is because there's a lot of information about the equation of state. It has to be monotonic, it has to be causal, it has to produce a maximum mass greater than 2 solar masses.
Ben,
Yeah?
how does your 10% number from Walter compare? Can you compare from that plot on the right at 1.4?
Yeah, so they're about the same roughly. I think that 10% is a 95%, so plus or minus 10% to 95% confidence, yeah. And that's roughly the same here. But then they said you couldn't, they did a linear fit of lambda as a function of m and said you couldn't measure the slope at all. But you can here. So that's the main advantage of using equation of state parameters. So, and I think they had 50 events or something like that, 20 to 50 events. So it's roughly equivalent at a specific mass.
So if I understand this correctly, you're taking, say, 50 events in the same mass bin, right? So then you have multiple mass bins?
So it's uniformly distributed from this dotted line to that dotted line. So it's just...
And then repeated in other bins.
I think he's confused about the contour lines that you're drawing.
Oh, so
How did you obtain it out?
the actual samples that we have are from, in our population, are from 1.2 to 1.6 solar masses.
Compare it with the whole range.
Yeah, but then the equation of state parameters will tell you what the radius should be at any mass. So that's how you can calculate it at different different masses.
So that's the error for a neutron star with radius around 12, between 12 and 14 kilometers. Right?
Yeah, so I'll show you.
If the true radius was 10 kilometers, how many neutron star, how many binaries do you need to see to get the same error bar?
So I'll show you a plot later, but it turns out it's roughly independent of what the true radius is. So the errors, for various reasons, the errors stay about the same regardless of what the actual equation of state is. I'll show a slide later. Okay, I'm not sure I'll say much about this, but we've compared results for using a Fisher matrix approximation versus MCMC approximation for calculating the tidal parameter for each star. If you just look at the loudest events in your population, you get roughly the same effect. I haven't looked at the quietest events, but the Fisher matrix breaks down for low SNR systems, so you'd expect it to get worse. But the dotted line and the solid lines are the difference between the Fisher matrix approximation and the MCMC simulation. So
for the Fisher matrix calculations, what did you do with the waveform? What was the waveform model?
Taylor
Especially
F2.
the boundary.
So it was just cut off at ISCO, which is the same that was used for the MCMC simulation.
There is quite a bit of discussion, both I think in the literature and within the LSD.
Mhm.
We know the result, that can significantly affect the results. And if you have very sharp cutoffs, there is too much of information.
Mhm.
You're telling the Fisher matrix calculation, my waveform is going to abruptly shut off at this point, and that's a
Yeah.
fantastic amount of information, and can give you much better estimates.
Yeah, but that was
We thought, unless the whole thing is outside the band, in which
Mhm.
case it doesn't matter.
Yeah, although, I mean, we use the Taylor F2 for both the MCMC and the Fisher matrix, so it
Yeah,
should.
that's true, but Fisher matrix, because it takes derivatives,
Mhm.
and that's where that information is coming from. But if you slightly smoothen this, and there are ways of doing it, there are a couple of papers in the literature to treat, all I'm saying is that Fisher matrix can give you good results if you treat the waveforms properly.
Mhm.
By abruptly cutting off, you are basically telling the code that there is a lot of information which isn't there.
I
Mhm.
think that argument also works for the MCMC approach as well. They're still putting
Sure,
the
I
artificial
agree.
cutoff.
I agree, but I think in the Fisher matrix case, it's probably a lot more because of the derivatives towards the end of the waveform. But if it is outside the band, then it doesn't matter.
Yeah,
I guess.
Okay.
Technically, there's no problem. It can be handled in a very
It can be handled.
non-singular way.
Mhm.
Because there was quite a lot of noise made about Fisher matrix that it was not a good approximation. And people have come around realizing that it's not really Fisher matrix fault. It's just that it was not being used correctly.
Mhm.
You can correct for any differences by treating the waveform model correctly.
Okay.
But for this particular calculation, how he generates the waveform and how you match it to the data is the same, whether or not you're doing Fisher or MCMC, right? And Fisher or MCMC is just your way of handling the likelihood function.
Yeah, so the Fisher matrix assumes a Gaussian distribution for the.
Right, for the likelihood function, but that doesn't affect how you evaluate each individual Markov point, right?
No, so the second step where you actually measure the equation of state parameters is done with MCMC.
Right. Oh, okay.
But then the first part where for each event you are trying to find the intrinsic parameters, the masses and the tidal parameter, that's done with either MCMC or Fisher matrix.
Oh, I see. Okay.
So I just comparing that.
Sorry,
So
I understand.
okay. So now I guess this is sort of related. So we don't have an exact model for the waveform. The point particle terms are just known to 3.5 PN order. The tidal correction looks like a 5 PN correction, or the leading tidal correction. So there's uncertainty in the 4 PN, 4.5 PN, 5 PN, et cetera, point particle terms. And what I'm showing you here are, there's different ways of writing the post-Newtonian waveform that, depending on how you truncate the series, you get a slightly different waveform. And these effects can be about as big as the tidal effect. So the difference in phase between how you write the waveform can be on the order of a cycle through the end of merger, and that's about the same effect as the tidal parameter. So what I'm showing you here are the results for if you inject different versions of the Taylor or the post-Newtonian waveform into your data and then recover it with a Taylor F2 waveform, you'll either overestimate or underestimate the tidal parameter, and that corresponds to a overestimation or underestimation in the pressure as a function of density. So this green band here is the result for the if you inject a Taylor T1 waveform and then assume that a Taylor F2 waveform is the true correct waveform, you overestimate the pressure. If you inject a Taylor T4 waveform, that's this blue band, and you end up underestimating the pressure. And these are 95% confidence bounds. So the error is about, the systematic error from not knowing the exact waveform is about as big as the statistical uncertainty. And
but
then,
if you injected and recovered using the same waveform model, I don't know whether you have the results, and maybe
yes,
it's very
that's
figured.
the red one here.
Only the red one.
Yeah.
But I think, irrespective of whether you use T1, T4, that would remain the same, I suppose. But you wouldn't have checked it because it's probably too expensive for your MCMC.
Oh, for using like Taylor T1.
Against T1 and
Okay.
T4 against T4.
Yeah.
Just to say that, oh, look, when you have the correct waveform model, the absolute errors are the same irrespective of what that waveform is.
Uh-huh.
That's a useful thing to have.
Okay.
In addition to saying that, oh, if you don't get the waveform model correct, then there will be bias in the estimation of parameters. That I think we know pretty well. But the
Okay.
related question is what I said earlier. Namely, if your waveform model is different, but the recovered waveform is the same as the injected one,
Uh-huh.
or the absolute error is the same. And I guess
Okay.
from experience I would say yes, that is the case, but it's good to confirm because these waveforms are so short.
So like playing around with the how you window the and the merger and stuff like that.
Yeah.
Okay. Yeah, and then
That's because it's basically a Newtonian effect.
It's mostly because these are pretty, I mean, how many number of cycles? You were talking about hundreds of cycles where it's actually important, right?
yeah.
It doesn't matter what the waveform family is. The absolute errors remain the same. What I mean is that red thing, which is Taylor F2, will be the same as Taylor T1, Taylor T1. If you did Taylor T1, Taylor T1.
Right, but now I'm wondering, but the Newtonian piece, I mean the tidal piece, that shows up in a very similar way across.
Exactly, that's why it will be the same.
That's it, so
So I'm basically saying yes. And also it's because it's a large number of cycles. There's a slight difference in the sense that Taylor T1 will end up at different frequency compared to Taylor T4 or Taylor T3 because they end, and that ending frequency sometimes may be important.
So it'll be good to know.
Depending on where, how
That
how
affects
quickly.
estimation.
Yeah. But I
Yeah.
think absolutely right.
Oh, sorry.
So on the face of that, like, so the top right-hand plot, for instance, if you were to imagine marginalizing over the uncertainties in the waveforms between over T1 to T4, it looks like your overall error increases by a number of factors. If you were to
Yeah.
take into account that spread. But what I was going to say is, with Bayesian analysis, I wonder what the results would be if you ask it what is the Bayes factor or the probability between models. I know that that's been done for injections between injecting, like exactly what you've done, injecting F2 or T2 and recovering with another one, and it tells you very positively which is the right model. I don't know the answer here as to whether it would be as powerful by putting in the extra tidal parameter space as well. But I wouldn't be surprised if it told you specifically which one of the models is far better than the other models
Uh-huh.
if you looked at the Bayes factor.
So you-
That far, you might want to also involve calibration or switch scale.
Yeah. I wouldn't marginalize, obviously. I would do what you are saying, which is to ask for which is a better model. Well, complete base factors for different models.
I mean, I can't remember the exact analysis that was done, but it was found that one model for hardware injections was many orders of magnitude far more likely than the other ones, and even marginalizing would have made no difference. You still pick surprised if your overall error is still the same after marginalizing of the models.
Okay. All right, yeah, so then I just, you can do the same thing with the radius or the tidal parameter. And then this just gives you, so not knowing the true waveform, you either overestimate or underestimate the radius by a couple kilometers. So you have to have the true waveform to be able to do this. So I guess this is not really that important. This is just showing you the results for if you observe a higher mass neutron star. So there's a couple possible neutron or pulsars with radii around, or masses around 2.4 solar masses, or possibly 2.7 solar masses, but those have large systematic uncertainties. And then essentially what that does is puts a lower bound on the radius or the pressure as a function of density. So this blue curve is if you know there's a 2.4 solar mass star, versus this red curve where you just know that there's a 1.93 solar mass star. And then I'm showing the same thing for the radius as a function of mass. So it just puts a tighter lower bound on the radius as a function of mass. So here I'm showing you the results for different true equations of state. So the one I showed you was MPA1. This is the 68% and 95% confidence, and then these are the other equations of state. This is a particularly soft equation of state. This is a very stiff equation of state. The errors are roughly independent of the true equation of state. And then this is the corresponding estimates of the radius as a function of mass and the tidal parameter as a function of mass. So you can see that it's roughly independent of what the true equation of state is. This is, I think, from a sample of 50 systems. And the error is always around a kilometer or so, 2 kilometers, something like that, independent of what the actual equation of state is.
It looks like it's tighter for the larger radius.
Yeah, for a certain, yeah. So.
For larger masses, I guess the reason why the errors get larger is because it's a higher frequency. But why for lower masses, the signal-to-noise ratio reduces?
So for higher masses, so you measure, it's always, the error is always smallest in the region where your actual data was. So for the tidal parameter, the error is always smallest between 1.2 and 1.6 solar masses. That's where your, sorry, here we go. That's where the actual data was from. And then the errors expand at higher masses and lower masses because you're not actually measuring that density region in your neutron star. Most of the masses in this density region. And then you use the prior information about the allowed shapes of the equation of state and causality and high mass observations to constrain what the behavior can be here. And then they get bigger here because we allow a wide range of possible low density equations of state. So we don't use like nuclear parameters or anything like that. That would really restrict the possibilities at low densities.
It will also reduce the signal-to-noise ratio anyways, right? If you go to very low masses, then the SNR will be smaller.
Yeah, if you have actual events that are there. But then the tidal effect grows because the tidal effect decreases as like 1 over m to the 5th power. So you're, if you actually see something at like 1 solar mass,
it actually should be that smaller.
Yeah, then your ability to measure the tidal parameter for a single event is much better for low mass systems and
except that, yeah, except it will go down because of signal-to-noise ratio. But not as strongly.
I mean, you'll see less events at a lower, for lower mass.
Effects, right? The tidal effect becomes bigger, but
Yeah.
then it pushed down to lower frequencies as well, isn't it?
It pushes to higher
Lower mass becomes bigger object, therefore smaller frequency.
So like
So that may be actually good news. Because the sensitivity will be better.
Yeah, you will go to lower frequencies.
The tidal effect goes to
for like
the lower
gravitational
frequency.
wave orbital dynamics
So, yeah,
would be
that's-
at higher frequencies for lower.
Yeah.
But the east code won't be,
If you just take like the short show kind of disco thing, that would be.
But you have a larger radius, so we want that trigger another.
Right, so the point particle dynamics are all shifting to higher frequencies, but the tidal contributions are coming in at lower frequencies.
Yes, that's exactly what I'm saying. The
But that's in
contribution
our,
LIGO
that's in our
effects
result.
are at lower frequencies than for higher masses.
Yes.
So that's the reason why you have better measurement. You should have better measurement ability for lower masses.
Yeah.
And also you have better sensitivity. The instrument inherently is more sensitive.
I think you have to keep in mind that those neutron stars don't exist.
It's fine.
I
We are just trying to qualitatively.
I mean, let's just keep that in mind. It's fine, you can measure them better, but they don't exist, so that's fine.
You don't think there's any one solar mass neutron stars?
No,
We will touch.
Jim?
I don't think so.
No, so there's
You don't think?
two of us against Satya. We can take you. But Satya.
You are against 900 people who are going to search for 0.9 solar mass
You
neutron
can
stars.
say, no, but say, you have to.
We can't just take two theories and say, oh no.
We're
you're
not
gonna search for
taking
them.
just theories, we're taking a quite substantial set of radio pulse.
Are you
masses.
suggesting that we shouldn't be searching for one solar mass
Yes,
neutron stars
I am.
in our data?
Yes, I am.
Not going to do that.
I wouldn't waste my time.
It would be a
But
good
you would say-
question
you
to
would-
ask
you
what the
would say
systematic
that-
uncertainty is in the minimum neutron star mass. And I think that's a question we should consider.
Sure. But I
Aren't
think
there
that-
one solar mass neutron star? I mean, you showed examples of.
I don't.
No,
Do you know about that?
Close to one.
There's like
You have
one.
but it has a very large error.
Okay,
You
that's
didn't
what
show
I
the error
thought.
bar.
Yeah.
Fine. Yeah. The error bars means that you go either way. So.
I'm not using, you can waste your time. I'm not gonna waste.
You're absolutely right, because we read a lot more
What does
temperature.
it cost you to extend your parameter range?
It costs a lot to go to lower masses.
Exactly.
It goes to m to the 5/3, where m is the lower mass.
The flip side
So
to-
it certainly helps
I wouldn't look for that.
if we can decide that no, there's no point in searching for 0.9 or 1, you can start at 1.2. It makes a big difference.
The
But
flip
I
side
don't
is
think-
the discovery impact of a 0.8 or 0.9 solar mass is going to far outweigh measuring a neutron star radius.
We don't care.
So
about
I think
this.
you shouldn't listen to any neutron
Thank
star.
you.
You should go look for it.
Yes.
If you find it,
No,
it will be
but-
much bigger news than anything else. we
No, but
talk
sorry,
about.
I'm not saying you should never do this, but I don't think you should do it initially.
No.
Initially, you put your effort where.
We don't know
you
where
think-
it is.
Well, I think I know where, sorry, I disagree with you. I've got a set of a range that is there from actual observations.
It's all from
where
our
people-
own
in
galaxy.
actual.
Our galaxy.
And you think neutron stars are different in other galaxies?
No, not necessarily. We have, it's a very small
Sorry,
sample, is all I'm saying.
That's folly.
Very small sample. Sample of.
We have a very small sample, that's true.
Well,
Okay,
we're-
I think
I
we
will still
can
put my
move this
effort where I
over
can afford
to
to
the,
do it.
after the
That's right.
discussion, so.
Okay. Yeah, so that was pretty much my last slide.
Okay, that's good.
So yeah, you can read that. Basically, I didn't mention this, but the overall uncertainties are about the same size as mass radius observations, about 1 kilometer if you stack the events. But the systematic errors are completely different, so that is a good thing. So we should understand the systematic errors for both systems, and they should agree. So it's a good check on mass radius observations. So that's all I had to say.
More questions, Sanjay?
So the systematic errors for point particle waveforms, I mean, that
Mhm.
looks like something that's one can attack using simulations. And what are people doing, and to work?
That's not so easy, right? Because you can't go much higher in EN expansions than where people are now. There's no one alive on this planet that's willing to go to the next order, I believe.
I thought
Maybe
some
a-
people.
But
Yeah,
maybe,
but-
the question was made to
People are
that.
working on
Will he do
4PM.
it? Will he live long enough to do it?
So I mean,
remember how long it took-
Mostly
how long it took to
field
do-
theory calculations,
Yeah.
which are algorithmic and.
Yeah, I guess that's true.
Yeah.